There are two main ways to measure salinity. The first is with a salinometer. It's a probe that has two barbs on the end, two electrodes, and electricity is sent through the probe. And the ability for the seawater to conduct electricity across those probes is one measure. The more dissolved ions in seawater, the better it will conduct electricity between the two barbs and higher salinity. The other way is through the Aquarius satellite. And the Aquarius satellite is in the sky and it measures conductivity in the upper few centimeters of seawater by detecting microwaves using a radiometer. And this, along with information about the temperature of seawater and how rough the surface of the surface waves are, they can calculate salinity pretty accurately. Here's a map of seawater. Move my face out of the way and see it's that same range. This does go pretty high up into 40, where there's high evaporation in the Mediterranean and lows down to 30 in the polar regions. So that is measuring periodically as it goes around the Earth our salinity data for the ocean basins. All right, so mid oceans are going to have high salinity, so in the middle of our ocean basins, but because of evaporation and because they're further away from input of fresh water by the rivers. This is a chart of the major constituents of seawater. I'm going to move my face out of the way here. I'm going to turn it off. The major constituents of seawater. So the top 6 most abundant ions in the ocean basins: chloride, sodium, sulfate, magnesium, calcium, and potassium. These make up 99% of the dissolved ions in seawater. The other 6 ions that round out the almost 100% would be the bicarbonate ion complex: bromide, strontium, boron, and fluoride. Those top 6 are the principle of constant proportions. That's based on those top 6. And what that says is these major constituents, these top 6, have the same proportion of the concentration proportion throughout our ocean basins. So that came about in 1819, that those were pretty constant throughout the ocean basins. The other ones, like the bicarbonate, for example, those can fluctuate because of organisms. So these top 6, though, they don't fluctuate. The balance of dissolved ions comes about from inputs and outputs into seawater. The inputs are from rivers bringing in dissolved ions from weathering of continental rocks. Volcanoes are going to also put ions into seawater. The mid-ocean ridge system and that exchange of water at the mid-ocean ridges. I mentioned metasomatism, different metamorphic processes in hot rocks is occurring, and there's going to be an ion exchange there. There also is the decay of rotting organic material. So that would put ions into the water. Output, so what pulls ions out of seawater, are going to be things like absorption and precipitation, and those are in conjunction with deposition of sediments on the seafloor. Then there would be output by sea spray, so that is splashing waves at the coastline. There can be minerals that are going to grow on like sea cliff areas, and so the sea spray takes ions out of the water. Biological uptake, biological processes are going to pull different cations and anions out of seawater, mostly to make their hard parts. And then sediments are kind of, especially clay, are kind of sticky, and those are going to pull ions out of seawater. There are gases dissolved in seawater. So one of those is nitrogen, another's oxygen, and carbon dioxide. There is also going to be argon, helium, neon, and other trace gases. That brings us up to 100%. The nitrogen and the oxygen are going to be in seawater in a high percentage here, and then some carbon dioxide. So those are those are the amounts in the atmosphere. Here it is in seawater. Those are churned into seawater from waves, are going to be pulling in atmospheric gases into the ocean basins, and that's what's pulling them in. And that's why notice the ratio kind of holds. Okay. Carbon dioxide and oxygen are dissolved in seawater, and those are important to look at because of biological activity. In the very, let's see, this is the top, say, 100 meters of seawater in the euphotic zone, where there's still some light, there's going to be more biological activity, especially photosynthesis in that top zone. So photosynthesis is going to remove carbon dioxide from seawater in the top part of our ocean. Then as respiration continues throughout the water column, carbon dioxide is going to increase. Just in the top bit, it will decrease. Oxygen is being produced in the euphotic zone, so there is an increase, and then it's going to drop off and be a pretty steady amount of oxygen in the water column. Oxygen actually sinks through the water column, and so there is a bit of an accumulation towards the bottom, and then there's also downwelling that brings oxygen to the bottom of the ocean.